to G of Z mod MZ. So this is like going down from SL5Z to SL5Z mod MZ. So this is for every M not 0. This is a finite index subgroup in gamma because this is a finite ring. And the congruent subgroup problem asks, and let's, okay, maybe definition. If H in gamma containing gamma M for some M, then H is called congruent subgroup. And the question, the congruent subgroup problem is every finite index subgroup a congruent subgroup. And this was asked already, or at least the people were interested in this kind of problem already in the 19th century, and already in the 19th century, they knew that the answer for gamma equal SL2Z, the answer is no. There are many subgroups of finite index which are not congruent subgroups. In some sense, we will see this in a quantitative way today, but why? Well, there are several proofs. I think that the one which is would teach you maybe the most is really to remember that SL2Z is essentially a free group. It has a free subgroup of finite index. Now, a free subgroup is mapped, for example, onto the alternating group, which is a simple group, right? The group of permutation, even permutation, the alternating group AN for every N. And on the other hand, if it will be, so take the kernel of such map, if the kernel will be a congruent subgroup, then the meaning would be that this alternating group is involved in this finite group, involved in the sense that it will be a quotient of a subgroup of it. But if you look at this type of group, when G is SL2, you can see that the only simple group which can be involved there are just SL2P. So this is kind of an hint for a good exercise, which I will not solve, which I will not do today, but this will be kind of think about it, write to yourself as a good exercise to think why the congruents are failed. But this was known already in the 19th century. I'm not sure who proved it first, but in the 60s, it was really Manic at the first, and then Bas Milnor and Lazar from a very influential kind of proof, but they knew, the story was, people usually attribute it to Manic and Bas Milnor and Lazar independently, but the independently is not completely independently. What I learned, I think Bas told me, that they erred at that time, no internet. I know that the young people cannot understand that the world can function without internet, but at that time they erred that Manic proved it, and then they prove it independently. But you know, if you know that something is true, it's a big it's a big help somehow. And so it's not completely independent. And then they use some ideas, Manic, Bas and Milnor and Serre. This was Bas, Lazard and Serre, I think, was the first who did independently. Anyway, in the 60s, I think it was really Manic who should really get most of the credit, even though he did only the very special case for SLDZ, D greater or equal 3, the answer is yes. And if you, those who were here in the first talk or listen to it over the recording, remember that I stressed that in many of the problems here, there is a difference between rank 1 and I rank, and that's exactly the story. The rank of SLN is n minus 1. So this is the rank 1 case, and this is the I rank case. The rank 1 negative, the I rank positive. But now, the more modern way to think about it is to do the following. Put on gamma two topologies. One is the profinite topology. So the profinite topology is, in order to put a topology in a group, you have to define bases of neighborhoods to all its points on a set. If this is a group, it's enough to define bases of neighborhoods of the identity, because if you know bases of neighborhoods of the identity, you can move them, you know, to all other points. And we can take a collection of finite index subgroups satisfying some easy axioms, and they define a topology. You can take all of them, you can take some of them. So here we define two topology. The first topology, the profinite topology, we take all of them. And once you have a topology on a group or on a set, the topological space can be complete or non-complete. Complete means that every Cauchy sequence converges, and incomplete, not every Cauchy sequence, but there is a standard procedure to complete a space, uniform space or metric space, and here the completion is simply the so-called profinite completion, which we denote gamma at, which is equal to the inverse limit of gamma mod n, where n runs over all the normal subgroups of finite index. All right, this is clearly an inverse system. We put in the reverse order, right? That the group is bigger if it's smaller. Gamma n is bigger if n is smaller. Gamma mod n, right? So you have a system. So the second topology is the congruence topology. The congruence topology, and here the basis of the topology is simply those principal congruent subgroup gamma m over n round over the positive integers. And then the completion that we will denote gamma hat is not such a good notation, because you think it's a closure. It's a closure. It's indeed the closure of gamma, but it's the closure in this topology. In this topology, the closure is this. Anyway, so this is the inverse limit of the quotient gamma mod gamma m. But you see, what is gamma mod gamma m? We know what is gamma mod gamma m is the image in G mod Z mod MZ. Now here, let me cheat you a bit, because if I would give a very precise talk, I have to say that I have to assume that G is simple, simply connected and simply connected, etc. So SLD satisfy all the good condition. Under this good condition, the image here is indeed the full G of Z mod MZ. For SLD, for example, that's a nice little exercise to see that SLD-Z is mapped onto SLD-Z mod MZ. For very general algebraic groups, there might be some problems here. So this is the inverse limit of G mod Z over MZ. Aha, but now this actually the important punch point, unfortunately, I have to move to the other blackboard. But this is the inverse limit of this. We can put the inverse limit inside. Now, what is the inverse limit of Z mod MZ? This is Z hat, right? If you think about it, Z mod MZ, if M runs over all M, MZ is the set of all finite index subgroups of Z. In fact, it's even the set of all ideals. Each one of them is an ideal in Z. So this inverse limit is not just a group, it's even a ring, right? And this is the completion of Z with respect to its profinite completion. All right, so how would we call it? Z hat. Like that, right? We'll put the hat here. So this is equal to G of Z hat. Okay. But what is Z hat, by the way? Z hat is the, I claim, is the product over all prime of ZP, where ZP is the ring of p-adic integers, the integers in the p-adic field. And what is this equality? What is this called in Hebrew or in English? The Chinese remainder theorem, right? This is just the Chinese remainder theorem, this equality, right? So this ring is a very interesting ring. I'm so tempted to give you a little exercise, and only next time, or no, don't think about during the talk, but you see, if this is a ring, I claim that the Z hat, this is a good exercise, even to the expert. I see Jan Minak, I saw you, I see Alan Reed. Even for you, if you don't know it, it's a good exercise, but don't think about it now. This is a ring, right? What is the invertible elements of this ring? I claim that this is exactly equal to P closure minus P, where P is the set of primes. You look at the set of primes, this is a subset of Z, right? Just a set of primes, all the prime numbers, 2, 3, 5, etc. This is a subset of Z, and this is a subset of Z hat, right? So I can look at the closure of these sets. I take the closure of this set, and then I drop out, I take out the primes out of the set. I claim that the invertible, that this is exactly the invertible elements of Z hat. And just like this equation is the Chinese remainder theorem, this is also a famous theorem in mathematics, much deeper. Remind me at the very end of the talk, I will tell you what's the name of this theorem. Okay, but let's continue. By the way, there is another theorem which is really involved here. The fact that the closure of the closure of gamma, like the congruence closure, the congruence completion of gamma with respect to the congruence topology is exactly G of Z hat. This is called the strong approximation theorem. And so, and in general, is a non-trivial theorem. This is the what? Which one? Good for you. This is exactly, this is writing Dirichlet theorem on existence of prime along arithmetic progressions is completely equivalent to this statement. This is a nice, cute way to write it as a one equation. That's not so known. I learned this from Furstenberg 50 years ago. Furstenberg has a wonderful proof that I will not spend the time now to show, that there exist infinitely many primes. And that proof, if a topological proof that there exist infinitely many primes. And I like this proof. I came to him. I was a kid that I wanted to do PhD on that. So instead of throwing me away from the room, he told me to start to read about profinite groups, and actually send me to some papers of Moshe Yarden, who was his first student in Israel, and it's just the right time to mention it because Moshe is celebrating right now his 80th birthday. Unfortunately, I'm missing this celebration in Israel, but and then Furstenberg told me that he tried to use this profinite version to prove the Dirichlet theorem, but he couldn't. There is no proof for the Dirichlet theorem based on this equation, but this equation is exactly the Dirichlet theorem. Okay, I prepare other things, so I don't want to stop here. So we have the congruent subgroup property. Now the congruent subgroup problem, modern version, so is the following. We have a map from gamma hat. So let's do it like that. We have a map from G hat. So gamma hat is G of Z hat outside to G of Z hat inside, which is onto the fact that it's onto is the strong approximation theorem. It's a non-trivial theorem, but it's a theorem which is true under some natural assumptions on G. And the question is, what is the kernel? And let's call C of G, but okay, for us the C will be the kernel, and the congruent subgroup problem is really about the kernel. Is C equal the identity? That's completely equivalent to the original problem to say that the two topologies are the same and then the two completions are the same. This is if and only if. As I told you last time, and I will illustrate this in few minutes, in the model, so the answer is here, the answer for SLDZ, the answer is yes, but already for some other ring of integers, it turns out that sometimes it's yes, but it's no, but it's really yes. Namely, the DC is finite. For example, if O is a ring of integers in a number field K, then nowadays we know, so this is a finite extension of Q, then the kernel, so let's say for D, so for D equal to, the story is sometime, I don't want to talk about that, but the kernel from SL, say D, for D grid O to SLDO, again, the same thing. You know, you can take the pro-finite, you can put the hat inside, the pro-finite completion of the ring O. When you take the inverse limit over all the ideals, then the kernel turns out to be the finite group of roots of unity in K. So it's a slightly more delicate issue. So it's if there are roots of unity, suddenly you get something. Sorry. Roots of unity, roots of unity already in Q, we have plus or minus 1. So I think you have to take modulo plus or minus 1. The non-trivial roots of unity. I hope I'm not. But anyway, it can be finite and non-trivial, but as you will see in few minutes, the kind of the deep applications of the congruent subgroup property already when this is finite. Now, the message that I'm basically going to show you today, that there are two extreme cases. Either the kernel, the congruence kernel, is very small, it's finite and central. It's just a central, in the center of gamma hat. So in particular, it's a small abelian group, or it's very huge. There was already an hint to this in the 80s. Well, independently, but I have to say that Melnikov and I prove it independently, but he was the first. Just at that time, he proved it in Russian, and it appeared in a Russian journal. As I said, no internet, and then till it was translated, I prove it in English. So Maybe people learned about it from me before they learned, but he was the first. But it was independently. Yeah. What? Sorry? Oh, sorry, yeah. Yeah, you're right. So here the kernel from SL to Z, you remember this is a huge group, it's kind of a free group to SL2 Z hat is equal to what's called F omega or F aleph naught, namely the free for finite group on countable number of generators. So you see, it's a huge group. If we mention Moshe Yarden, then in all this area of field arithmetic and Galva theory, this group play a role, Iwasawa theorem, etc., a countable number of generators. So you see that the kernel is trivial or finite or very small in that and huge in D, and in a way, this is a good hint to what we are going to see later. But before we'll go, which will be the second part of my talk, the first one part of my talk, I want to sketch the proof of a beautiful result, which for some reason seems to be not known enough, except of a small circle of experts, and I can guess why this is maybe not known enough, but I think it's still beautiful. And this is the congruent. So from now on, we say that gamma is congruent subgroup property, not congruent subgroup problem, but it has the congruent subgroup property if this kernel is finite, okay? Even though, to be honest, for the original problem, if it's finite and non-trivial, then the original problem, you have a negative answer, right? There are some groups which are not congruence, subgroup, which made the profinite completion bigger than the congruence completion, slightly bigger. But still, we call it, by now, it's essentially understood the reason for that. There are delicate arithmetic reasons, so they're part of the game. What I want to prove today, to show a sketch of proof, I think it's due to Ser. It appears for the first time in some Lubotzky talk, I think, of Ser, and then in a paper of Bas Milner on Ser, and then in a full generality in a paper of Raghunathan. And this is the statement. I see, Guy, that I have a youngster in my audience. That's great. That congruent subgroup property implies superrigidity. I wish I would know the other direction. I don't. The other direction would be a dramatic, because the other direction would show us, for example, that lattices in SPN1 is the congruent subgroup property. And I showed you last time that if lattices in SPN1 have congruent subgroup property, even if one of them, then this will give a solution to Gromov problem, to Gromov question that there exists non-residually finite hyperbolic group. I want to sketch proof of that. I will just go. So okay, let me say what is superrigidity. Superrigidity means superrigidity. Again, I will be a little bit sloppy here. Means that if you have a representation, well, maybe I'll let him say it a little bit precisely, and then if you have a map from any representation from gamma to GLNC is a restriction up to finite index, namely there exists a finite index subgroup of gamma such that this representation is okay, assume that the closure of gamma is not compact. For example, well, I don't want to explain it. Up to finite index is a restriction of an algebraic representation of G to GLNC. So every you see, a gamma is the ring of is the integral point of some algebraic groups. For example, think about gamma equal SL5Z. Okay, so we say that every representation of SL5Z is essentially an algebraic representation of SL5 over R, or over the complex number. Now, representation of SL5 over the real numbers, over the complex number, are very well understood. This is a classical theory of highest weight, depending on the root system of the group. They are fully classified and understood. Now, if you take a discrete group, then usually, like, think about how wrong is this theorem for SL2Z. SL2Z is a free group. So it's essentially a free group. So its representation theory is completely wild. You know, you can send the free group to everything, right? It has infinitely many different representation in every dimension. Here, for example, a corollary is that you have only finitely many non-equivalent representation in every dimension. We will talk about this in a quantitative way in a minute, and not in a minute, in a few minutes. So now we say that every representation is essentially algebraic representation. Of course, there are representations which are not like that. For example, take finite groups, a finite quotient, and take representation of the finite quotient. But representation of finite quotient, the theorem is clearly true because the kernel is of finite index. Okay, you restrict to a finite index and you get a trivial representation. Trivial representation is algebraic representation, not very interesting one. So let me, I will sketch a proof when the representation of gamma is to GLNQ, already to over the rationals. But this is NQ, it's not, so this is maybe DQ, SLDZ. I mean, and the passing from the general case to this case is a standard commutative algebra specialization argument. The meat is here. So, and in fact, it just will be a question of formalities. Let's assume that it's S2 SLNQ. I can always embed GLN inside SLN plus 1 if I want. So let's assume that we have this is the representation. Okay, so now let me sketch the proof. Why such representation is algebraic? And before I'll sketch a proof, why this is not so well known. You know, you all know, I mean, many of you know the superrigidity theorem of Margulis, etc. The superrigidity of Margulis caused this theorem will be maybe less interesting because Margulis proved superrigidity for lattices in high rank Lie groups. So people, and deduce the arithmeticity of the lattices from there. Here we start with a lattice that we know that it's arithmetic. In order to know the congruence subgroup property, okay, it should be high rank, then we already know by Margulis, by completely different method. But still, I think that the method of proof is very interesting and teaches you something. So let me indicate the proof why this. Okay, so now I will have to use few facts, but so I will tell you the story now. One, gamma is finitely generated. All these arithmetic groups are always finitely generated groups. And therefore, let's say that gamma is generated by G1 up to GL. Now, we look at row G1 up to row GL, well, also with the inverses, say. And now these are matrices in SLN Q, right? This is my rho. Rho is the representation that I want to show that this representation is essentially algebraic. It's an algebraic representation on some finite index subgroup. Now, so I have finitely many matrices. So now for every P, every prime P, such that these matrices, all of them are P integral. What does it mean? Look at these matrices. Look at all their coefficients. Only finitely many primes appear in the denominator, right? The numerator is the denominator. In the denominator of these matrices, only finite appear. So for almost every prime does not appear there. So the numbers that we see are what's called P integral, namely the denominator is not divisible by P. So the image, so I can take SLN Q and I can embed it to SLN QP. That I can do for every prime P. But if all of them are P integral, then for such P, and this is almost all P, I need only one. But for such P, rho is really a representation from our gamma to GLN ZP, because all the elements of the generators will go to p-adic integers. If I multiply them, they are still p-adic integers, right? And it's true for them and for their inverses, so every multiplication. So I really have a representation into GLN ZP. But now we assume that we have the congruent subgroup property. I erased the important theorem. We assume that we have the congruent subgroup property. So what do we have here? What do we have here? So we have, you see, I have a representation from gamma to SLN to GLN. Well, it's really even SLN, right? So I have a representation of gamma to SLN ZP suddenly. This is the n by n matrices over the p-adic integers. This is a profinite group. Now, if you have a map from your group gamma to a profinite group, then that's abstract nonsense, and you can extend the representation to the profinite completion to gamma. Therefore, I have rho hat, if you want, from gamma hat to SLN ZP. But now I want to use the congruent subgroup property. The congruent subgroup property tells me that gamma hat, right, is essentially up to finite index. And you'll see in a minute that the finite index, it's not really important, because by moving to a finite index subgroup, I'm going to move several times to a finite index subgroup. I can move to a finite index subgroup here, which does not intersect this finite kernel, right? So up to finite index, it's equal to a finite index subgroup of this, okay? And this one is a product. Now I don't want to write product over P because here I specify a specific P, so I will write L. L is a prime, and this is G of ZL, right? I probably could do better if I would choose that prime to be L and this P, but doesn't matter. Okay, now let's look at each one of these groups. now I claim that G of ZL, this is a p-adic analytic, this is a group like, it's a p-adic analytic group, a compact p-adic analytic group. Its G is an algebraic group, is SL5. So this is like SL5 of ZL. Here is a fact that a group like that is virtually pro-L. What does it mean, virtually pro-L? We know what is a pro-finite group. Pro-finite group is the inverse limit of finite groups. A pro-L group is the inverse limit of finite L group. Right? In the theory of pro-finite groups, there is like the P-silos are pro-P groups, right? So it's a pro-L group, and GZL is virtually pro-L. Namely, it has a finite index subgroup, which is pro-L. Proof, you have to do it only for SL M, for any M, for SL MZL. And that's a little not complicated exercise. So it's always essentially a pro-L group. Moreover, it is and virtually torsion-free, namely, it has a finite index subgroup which is torsion-free. In fact, if you look at the congruent subgroup modulo L, it's already pro-L and torsion-free. There is a nice book by Marcus de Sotoya, Vinoa Mann, Dan Siegel, and Dixon about analytic pro-P group. You can see all these facts in there. Okay, so what it means here. So you see now we have a map from here to SLNZP. Okay. Take each one of these ZL. What happened with each one of these ZL? If L is different than P, it has a finite index subgroup which is pro-L. This one has a finite index subgroup which is pro-P. The image of pro-L in a pro-P is trivial, right? It's like if L is different than P, if you take it's like for finite group, if you take a map from an L group to a P group, it must go to the identity. There is no other way. So the L part, when it comes here, the image of this must be finite. But this group is almost pro-L. Above the pro-L is finite. So the image of each piece, the image of this piece when L is different than P, the image of this piece here is finite. Right? But maybe I have to say it first. By replacing gamma with a smaller group, I could assume that the image here is already inside the torsion-free part of this group. Right? So again, by going slightly more to a finite index subgroup, it is in the torsion-free part of this group. Okay, so but now the image for every L different than P is finite and in the torsion-free part, so it's trivial. So the image of all these GZL in the pro-P group, in this p-adic analytic group, up to after passing to a finite index subgroup is completely trivial. So what we left with? So all this means that after passing to finite index subgroup, we are left that rho hat is really only from GZP to SLNZP. That's really the essence. There is nothing else. All the other things is kind of a noise that by going to a finite index subgroup we can get rid of. Okay. Okay. Now what do we have? we have a map between two periodic analytic Lie groups. We have a map. This is a Lie group over the periodic. This is a Lie group over a periodic. And this is fairly standard fact that every map between, I have to be careful here, between simple Lie group over the periodic, this is just like every map between simple Lie groups, which is continuous, and this is continuous, without continuity maybe, is already analytic. And it's already algebraic. Okay, so here we need a little bit from the theory of a Lie group or periodic Lie group, but it's the same like real Lie group that you see I have a map from this simple periodic Lie group to a simple periodic Lie group. Every map, every continuous map between two Lie groups is analytic and even algebraic. And this finishes the proof. Or at least the essential part of the proof. I have to explain why it's algebraic over the rational, etc., etc. Okay, but you see how the congruence property plays the role here, and you see that we don't care about the finite kernel, right? By going to a finite index subgroup, we got rid of finite kernel. If we would have an infinite kernel in the congruence property, then the story will be different. Okay. So I'm only halfway through and more than half of my time already gone. Okay, so let me go now very quickly to the second part of my talk. And this is the congruent subgroup property and boundedness property, because this type of, this part will be very relevant also for a few other talks that will come later on in the next few weeks in the seminar. So let me give you, because I'm now really worried about the time, let me give you various boundedness and finiteness properties of groups. The one which is maybe the most famous, now gamma any group, not necessarily arithmetic, gamma any, say, finitely generated group. So now some definitions. One, gamma is called boundedly generated. The kitzur BG, if there exists, I don't know, gamma 1 up to gamma L in gamma, such that for every G in gamma, G equal to gamma 1 to the E1 up to gamma, I can write it like that it's a product really, okay, gamma 1 to the E1 up to gamma L to the EL, where EI are integers. So it's a product of finitely many cyclic groups, not direct product. They don't commute with each other. Otherwise, it would be a commutative group. It's just a product. Or if you want and to write it in a different way, gamma is simply the product of the subgroup generated by gamma 1 with the subgroup generated. It's a product of finitely many cyclic groups, but not direct product. They don't commute with each other. So this is kind of a strong finiteness theorem. By the way, about profinite group, if say K profinite group, then K, we say it's boundedly generated if K is equal C1, C2 up to CL, where CI are the so-called procyclic group. Namely, these are groups which are generated topologically by one element. Like cyclic group, you take a cyclic, you take an element, you take the group generated by it, and you take the closure. Then you get a procyclic group, and then the profinite group is called boundedly generated if it's a product of procyclic. easy exercise. If gamma is boundedly generated, then its pro-finite completion is also boundedly generated. Till recently, we thought that the converse is also true, but it turns out that the converse is not true. But let me keep this for later. I don't know if I've managed to get to that today. Okay, so this is one boundary condition. I want to write you several because I see that I won't have time to talk about each one of them separately. Again, gamma is still any finitely generated group. Let's denote Sn of gamma to be the number of subgroup of gamma of index at most n. I want to count how many subgroups of index n gamma is. This is called the subgroup growth of gamma. You may heard you may heard about this, but if you have not, you probably heard about the Milnor, Gromov growth of groups that you count. You start with a finitely many generators, and you count how many elements you have of length n's. This is kind of measurement of the size of the group from below. Here we measure the size of the group from above. Do we have a lot of subgroups or very few? For Z, we have only very few, right? We have a unique subgroup of every index, so this grows linearly with n. On the other hand, for the free group, here is the next exercise. Well, it was a theorem of Marshall-Hall, but by now the standard, I think we could really say that this exercise, Sn of gamma, is something like, if I remember correctly, n times n. So if gamma is the free group on L generators, is n times n factorial to the L minus 1. So you see that if it's a non-abelian free group, this is a super exponential growth. It grows faster than exponential. Let me put right away, if gamma is arithmetic, I mean like the kind of groups we care about, denote Cn of gamma to be the number of subgroup H of gamma of finite index of index n, but that H is congruent subgroup and the index is at most n. How many congruent subgroups we have? Here are several more invariant for general group denoted by Bn of gamma. I will do it in the language of profinite to avoid, take the profinite completion of gamma divided by the group, by the n power, the group generated by the n power. Why do it with profinite and not with this? I could do it with the group itself, but then I will have to say something. Well, here I also have to say it actually. If you look at a discrete group, you divide it by the n power, it's not necessarily a finite group because of the negative answer to the Berenstain problem. If you do it in the profinite category, this is a finite group because of Zelmanov's solution to the restricted Berenstain problem. But you can relate it to the original group. It's in fact equal to the order of the maximal finite quotient of exponent n of gamma. So it's kind of a measurement how if you divide the group by the n power, how it grows. You take n and n bigger and bigger. So you can look at this. And there is another way to measure the growth of gamma. Maybe again, it will be a little bit more convenient to me to speak in the language of the profinite. Dn of gamma is the maximum over d of h, where d of h, d is always the number of generators. Now, if this is a profinite group, then this is generators as a topological group. How many generators you need to generate is a topological group. When h go H finite index in gamma hat, and H is of index at most n. Okay, I don't have to say finite index, but it's a subgroup index at most n in gamma hat. So how fast the number of generators go? Again, for a free group, it goes, in this case, it goes linearly. It's well known that the number of generators of the free group of index n is linear in n in a non-abelian free group. So, okay, I think I will stop here. I can present several others, but I want right away to write you one theorem, and then I will give an indication of the proof. Like I'll give you, again, only the crucial ingredient in the proof. It's really, I'll write it as a one theorem, but it's really a combination of several theorems. Which, okay, maybe just before the theorem, one preparation theorem. This is a theorem. Yeah, in this formulation, I prove it. Actually, most of my talk is based on a paper I wrote. But when was that? Oh my God. This is Invenzione 95. But I'll some of it based on other people, I will mention that. First of all, the first theorem is if it's gamma arithmetic, then there exist two constants, say A and A, such that Cn of gamma, the number of congruent subgroups of gamma, is at least n to the little a log n divided by log n, and at most n to the capital A log n divided by log n. It's actually a very interesting story here, but but this is not the direction I talk today. In that paper, I ended the paper by asking the question, are they equal in the following sense? Like, look at a log. So what we get is that log Cn of gamma is like it grows right below and up, like log square n divided by log n, right? And I ask whether is there a limit to this, whether we can really close it. And the answer, that's what I asked there. By now, I work on it. I spend a lot of time of my life, maybe too much, working on that with Goldfeld and Pieber and Nikolov, and now we have a complete understanding, at least modulo the generalized Riemann hypothesis. In many cases, we can prove it without independently of the Riemann hypothesis. Like even for SL2Z, we were so happy that we proved that the limit of this is, if I remember correctly, is 3 minus, no, you see, I work on it. I know it's, what's the number? It's a concrete number, something like yeah, I think, yeah, 3 minus 2 square root 2 divided by 4. Exact number. And at that time, we were so happy because we thought if Poincaré was very interested in congruent subgroups and non-congruent subgroups, and then we thought, Poincaré would come, this will interest him. And this this work, which gave the precise growth, needs Bombieri Riemann hypothesis on the average. So it really uses quite a lot of number theory for that. Yeah. What? Yes. In fact, we know to compute it exactly now. Modulo in the most general case, modulo Riemann general Riemann hypothesis using the root system of the algebraic group. Like it's there is an invariant cum, which is the number of positive root divided by the rank. Can you put it? It was a very, very complicated one. Anyway, but I mean, for today, I just need that this is the rate of growth. Why do I need it? Because now I want to give you the theorem that I wanted to present today all together. I mean, and as I said, it's kind of many theorems, and basic, but with the same message. And the message is that if the congruent subgroup property fails, it dramatically fails. It's not like just little bit fail. So theorem, so if gamma arithmetic say gamma g of z, and I will let me assume for that G is a simple group over the rational. Or for the expert, I would say you have to like that it satisfies the Margulis-Platonov conjecture, which is known in most cases, but let me not talk about it. Then the following are equivalent. 1, gamma is the congruent subgroup property. 2, gamma hat is boundedly generated. Gamma hat. So let me say something about this. We knew for many years by now that if gamma boundedly generated implies the congruent subgroup property. This was proved, usually people say that it was proved independently by Rapinchuk and by me, but I should be honest here. Rapinchuk wrote a preprint and he conjectured that. And then it's amazing that at that time where the curtain, iron curtain, how you say in English? Curtain iron between the USSR was closed. For some reason, in Jerusalem, we got this sequence of preprints which came from Minsk, Belarusian, and I was lucky enough that I went over them. I remember them a bit blue. And then there was a preprint by Rapinchuk who conjectured that the bounded generation implied the congruent subproperty and proved something along the way. I was interested actually at that time with the other property that I'm going to write down. But in that paper, he had exactly what I needed for me, and I could see how to finish it. Meanwhile, he also was able to prove this. So people say that we prove it independently, but I should admit that he was independent of me. I was not independent of him. I will formulate something in a minute, which in that paper I called it Rapinchuk lemma, that is really due to him, and it's kind of substantial to all this. Number 3 is let's see the Sn. You see that Sn of, let's talk about that log of Sn of gamma is little o of log square n. Now that's kind of an amazing story, the equivalence of number 3. Why? Because you see, I just told you that log of the congruent subgroup property, a log of the congruent subgroup is something like log square n divided by log n. So I guess maybe you're not impressed, but you see, if it's just slightly less than log square, you already have the congruent subgroup property. Let's say it in the negative. Assume you don't have the congruent subgroup property, then you have at least log square n in the logarithmic scaling. Namely, there are many more non-congruent subgroups than than congruent subgroups. You see, if the congruent subgroup problem fails, then and you take a random subgroup of index n, it's surely or very likely, like 99%, is going to be a non-congruent subgroup. There are many more non-congruent subgroups than congruent subgroups. You understand the message? And the same is also with the other properties. 4 is that Bn of gamma grows polynomially, is at most n to the constant if the congruent subgroup property fails. Holds. So if it fails, it's not polynomial. In fact, this is even equivalent that Bn of gamma is okay, I didn't put Bn of gamma is at most O depending on epsilon of e to the n to the epsilon. You see, so it means that really, if you think about it, it means that if the congruent subgroup property fails, it fails dramatically and it grows so much faster than the expected one. And again, number 6 would be the d hat of gamma will be O of log n divided by log n, and 7 will be the dn of gamma. You see, in the case of congruent subgroups, this is the truth. But even if it is O of log n, we already can deduce the congruent subgroup property. You see, so these are, it doesn't matter each one separately, but the message is that if the congruent subgroup fail, it fails dramatically with many groups. Now, I don't have time to give you, and to be honest, it's not so interesting to see the proof of each one of these theorems. I just want to give you the basic idea why this is true, that if the congruent subgroup property fails, then it fails dramatically. And the key for that is again, Jean-Pierre Serre's approach to the congruent subgroup property. Because I want to talk to you, even though I've only 10 minutes, I think it should be enough, on another way to formulate the congruent subgroup property. And this is the aldelic way. Let's look, instead of looking at gamma, look at G of Q. So instead of looking at GLD of Z, look at the group GLD of Q. And define two topologies as also two topologies. One, I can define topology on the group of rational points. One topology is we call it the arithmetic topology, which is the topology defined by all the finite index subgroups of gamma and also their conjugate, etc. You know, if something is open, everything else. The other one will be the congruence topology. I can think of it, just think of it. You see that by just changing the mode of thinking, doing exactly the same thing, but changing the mode of thinking and thinking about the rational group rather than the integral group, I can think of this with two topologies, the arithmetic topology and the congruence topology. And then I can complete it. So I have GQ hat. Now we have to be careful here because this is not really the profinite completion. GQ, like SLD, Q has no finite index subgroup. You cannot take the profinite completion of it. It's really completion with respect to the arithmetic topology. And I have the completion with respect to the congruence topology. By the way, it's not so important. It's a little important for us, but this is because of the strong approximation. This is the G over the ring of finite adels of Q. If you know what it means, if you don't know, don't worry about that. And the same kernel as before will show up here. So we just change a bit the way we think about the problem. But this makes a big difference, which enables to prove this theorem. Why? Because assume, so what we really have to prove, in order to prove all these parts of the theorem, what we really have to prove? We really have to prove that if the congruent subgroup property holds, okay, you have to prove the positive part. That's relatively not, you have to do it, but that's standard group theory. What the interesting part is to prove if the congruent subgroup fails, you want to prove that the profinite completion is very big. it has many subgroups of finite index, etc. But what do I know? The only thing I know that it fails. I know that there are some non-congruent subgroups. Why? Why should I know that there are so many? So here is the trick, and this is the following. Let's look now. You see C. Okay, look at C now. If at the group, you see now the group GQ, which is an infinite simple group like SLDQ, essentially simple, right? The group CQ acts on C by conjugation because GQ sits here. Now there are two possibilities. Assume it acts trivially by conjugation. If trivially, then C is central. Why? Because GQ is dense here, by definition. And if by conjugation it centralizes C, then C is in the center, right? Everything acts trivially. So this is a central extension of this group. And this group is an adelic group. Adelic group are well understood, and central extension, it's a deep theory. I mean, I'm kind of throwing under the carpet a lot of mathematics, but central extension of adelic group are known to be finite, and even people can compute them. Metaplectic is a Prasad, Rapin. I mean, it started with many great mathematicians. Eventually, I think Prasad and Rapinchuk did the most general war. Anyway, but the fact that central extension are finite, this was known long ago. So if it's central, it's finite, which means that we have the congruence property. So assume now it's not central. If it's not central, let's okay, I'll be cheat a bit, but take some F and M. I take some finite simple group, which is a quotient of C. It can be a abelian simple group or non-abelian. Okay? And the kernel is M. So I have M is a finite index subgroup, normal subgroup of C, which is maximal with respect to normal subgroup. Now, GQ acts on C, so I can look, let's call N to be the intersection of MG over all G in GQ. Now, there are two possibilities. If N is still a finite index in C, then GQ acts on C mod N, which is a finite group, right? But GQ is a simple group, infinite simple group. Our simple group can act on a finite group trivially. So it's central. So we are not there. So we are now in the case that this is an infinite group. But what is really, now think about that. If you look at, if you have that C mod M is a finite simple group, and then C mod intersection of MG, and it's a little exercise that it must be F to the something, some power of F, but if it will be finite power, we are in the finite case. So it must be infinite power. Infinitely many copies of F lies down below, which means that if we have, so what's the corollary? Corollary is a kind of a version, what's called Rapinchuk lemma is more complicated than that, but this is the essence of it, that if congruent subgroup property fails, then below C in the kernel, just not C is mapped onto a product of infinitely many copies of the same finite simple group. In particular, for example, C is not finitely generated as a topological group. So you see, we already see that there is a big dichotomy. Either the C is central and finite, which is the affirmative solution to the congruence property, or C is not, it cannot be even finitely generated as a profinite group even. So it's a huge group suddenly you see there. If it's a huge group, then you can also see here that gamma hat is mapped onto a group which looks like that. Group which looks like that. It has delta, which is like G of Z hat at the top, but at the bottom, F to the infinity, and even more. You see? So we see that gamma hat is a huge group. We find suddenly such F to the infinity at the bottom of it, and not too far in the bottom, because this part we understand. Okay, so the rest is working with this fact and deducing that this would give you not boundedly generated, this would give you this. We need more, it's not such a trivial, even to continue, but from now on is a more standard group theory. The essential point is exactly this one, that if the congruence Subgroup property fails, then it dramatically fails. You have at the bottom a kind of you have how you call it, kind of a layer which is a Cartesian product of the same finite simple group infinitely many times. Okay, I almost did what I wanted. You know, I could always say more, but our time is over. And what will happen next time is that Nir Avni will show connection with model theory. The model theory is sometimes a language, and as you can see, some deep boundedness properties are hidden there, and Chen Meiri after that, and then Rapinchuk I mentioned already last time in a different context that he and Jim Borain and others proved recently that uniform lattices are not boundedly generated. Some of them do have the congruence subgroup property, which exactly shows why the congruence subgroup property is not equivalent to bounded generation. But Chen Meiri and Nir Avni may suggest some new bounded generation which can be replacement to all this, and maybe can be the key to solve more cases of the congruence subgroup. Okay. We'll see. Thank you very much, and also to all the people at home. Thank you very much for being with us. Yeah, okay. Some people ask me about recording. So all the lectures are recorded, and you can find them on the website of the seminar, but you have to go down. It's sometimes not easy to find because you have to go to the very bottom of the web page to see the lectures and the previous lectures. Thank you.
Hi, Alex.
Yeah.
Hi, it's Jimbo. Hi, how are you?
Oh, Jimbo, you are here. I just talked about you. Yeah.
Yeah. In the midnight, but I'm still, I'm really.
Oh, for you it's midnight. Oh my God. He's in China.
Yeah, it's midnight. Yeah, that's right. Yeah. Yeah, okay. So are you going to say something about the metaplectic kernel in the future?
Not really. At least I will take a rest a little bit now. And the next few talks will be, maybe at some point we can come to that. I don't know. But the metaplectic, I mean, it's extremely delicate issue and deep, etc., but the metaplectic is the determination, what is this exactly the finite kernel? Now we kind of think about it, just finite is finite, and we don't go to this, at least as of now, this is not the direction that we are taking.
I see. Yeah.
Later on.
Yeah. So just one quick question. So you have written 7 equivalent formulations starting from congruent subgroup property and the bounded generation. So you said, okay, so it's still there. So you said that the third one was proved by Andre, right? But which one you will have your credit or something? I mean, I'm not quite sure about this. So you prove the rest of them or something? Sorry?
No, I didn't understand the question, sorry.
No, yes. So on the chalkboard, you wrote 7 equivalent formulations. The first one is congruent subgroup property, and the second one is bounded generation, that one.
Yeah.
So
yeah,
you said that
all the others are in my paper, in this Invenzione paper that I mentioned.
Yes.
They're all there. Yeah, I prove this, but to be honest, the essential, the key is what I called in that paper. I call Rapinchuk lemma because that was the little argument that I found in that preprint of Rapinchuk, and this took me this gave me a lot of mileage.
I see. But you said the third one was also proved by yourself, right? This log of Sn gamma.
Yeah. I mean, all this I proved. Yeah, all this I proved. I still had to do some work even after Rapinchuk, but somehow I remember the minute I saw there was I knew to handle all this if this F is a finite simple non-abelian simple group. Then I knew to handle everything without Rapinchuk, but somehow the abelian caused troubles more than the non-abelian for a technical strain reason, and I didn't know how to do it. And then when I saw the preprint of Andre, it was I don't know if Andre is with us, but for me it was like, there was a spark that that's exactly what I needed.
I see. Yeah, I see. Yeah. Okay, I might also ask him about this history. I mean, maybe he'll tell me something else. I mean, yeah, yeah. Okay. Anyway, so thanks for that.
Okay, thank you, and go to sleep. You deserve sleeping.
Yeah, that's right. Okay, so thank you. Bye bye. Yeah.
Okay, take care. Bye.
Bye.
Jerome, I see you. You also here. What's the time for you now?
But I'm in Canada for the moment. It's 20
Oh,
past.
in Canada, that's not fair.
Yeah, next week it will be 5 a.m. so might not be there.
Where are you?
Next week I will be in New Zealand again, so then it will be 5 a.m. Then I might not come. I will see.
I see. Okay. Yeah. Okay. Thank you for coming. Thank you.
See you, Alex.
Bye.
Bye.
No, it's no.